To chapter 11, and we started talking about and what we're really talking about in this chapter here is electrons, basically about electron configuration, sort of where they are, and really the idea of what we'll talk about here is electrons, as they sort of transition from one energy level to the next. As we talked a little bit about last time, it does require obviously a certain amount of energy to do those transitions, regardless of sort of which way you're going. If you're going sort of lower energy to higher energy, they need to absorb energy, which is an endothermic type process. Energy needs to be absorbed by the atom to excite those electrons, kind of like what you did when you did flame tests the other week and you stuck the thing into the flame. Obviously, you excited all the electrons with all that energy. And what will eventually happen as well, though, is things in chemistry do like to be in a lower state of energy. So the electron will sort of relax back down to lower energy states. So they'll go from higher energy states to lower energy states. The result of that is they do have to release some energy to do so. And that is what's referred to as being sort of exothermic for the atom. It will give off that energy to allow the electrons to come back down to whatever energy level they sort of end up with. As the energy is either being absorbed or even really being released, a lot of times it's released as sort of a photon of light with a specific wavelength. So I think we finished up last time sort of talking about waves and some different aspects of waves. First off, as you can see there, the wavelength with its lambda is really the distance between obviously two peaks or two troughs there. We also have the amplitude, which is sort of from the midline distance to the top here. We also talked about the frequency, which is new here. And the frequency is basically how many times per second a wave sort of passes through a particular point. Remember that the frequency has units of 1/seconds or reciprocal seconds. Also, a reciprocal second is also a hertz. So that's also a very common unit of frequency, and they are basically the same thing. So a reciprocal second is basically the same as a hertz. Interchanged in terms of the units associated with it. One sort of aspect that we look at sort of the speed of a wave, which is a lot of times given in meters per second. So a lot of times when we're dealing with waves in terms of wavelengths, meters is a very common unit that we use a lot. Centimeters and nanometers are also very common units that we use for wave. Reminder again that there are 100 centimeters in 1 meter. And in 1 nanometer, there are 10 to the minus 9 meters, or 1 times 10 to the minus 9 meters is equal to 1 nanometer. Again, that flip around the wrong way and go 10 to the minus 9 nanometers meters. So that again is the proper way to do it. And it is like 1 times 10 to the minus 9. So we're just going to pick up here where we kind of left off, I think, and continue talking about radiation and energy. And we talked about sort of energy being moved through space in the form of these waves. And again, there is a relationship between sort of the wavelength and the energy associated with it and the frequency. So I think we might have talked about it last time, but if we have a very short wavelength, a high frequency, and that usually is a high energy sort of wave. And again, that's something like we're just going to go. If we have longer wavelengths and a lower frequency, that is usually lower in energy. So there is sort of a relationship between the wavelength that's coming off for a photon of light and sort of the energy associated with it. Electromagnetic radiation can be characterized as sort of waves and also particles. So we talked, I think, about it as well. Sign of the dual nature of light, sort of there's wave and particle type of relationships that occur. So something like electrons, which is what we're focusing in on this chapter, which is a particle, as we'll talk about a little bit later on, can have wave-like function and sort of behave like waves. And waves can also be sort of particle-like functions as well, with a wave or a photon light just being like a stream of particles sort of happening as well. So one can think of, like I said, a beam of light is traveling through space as these sort of packets of energy. We also talked about the idea of as energy is either absorbed or sort of given off, is this idea of quantized sort of energy, where again, we talked about the idea is essentially that, an electron, for example, will gain or lose enough energy to fully make the transition from one energy level to the next. They won't find themselves halfway between energy levels or anything like that. So they really do sort of gain and lose energy and whole number ratios that allow them to fully make those transitions. And the idea of quantized energy, as we talked about, is the idea kind of like stairs, as we'll see shortly. Again, either you're on one level or the next level. You never really find yourself sort of in between stairs or anything like that. And that's sort of how electrons transition. And as I mentioned, the longer the wavelength of light, the lower the energy, and the lower the frequency, and the higher energy, shorter wavelength, much higher energy associated with those type of come off. See here, even with colors, for example, and we do see colors like in the flame tests, when the wavelength of light that's coming off is in the visible part of the spectrum, where we see colors like red, orange, yellow, blue, green, indigo, and violet. And even with colors, there's a difference in terms of energy. As you can see here, the red wavelength is a lot longer than the blue wavelength here. So our wavelength for red is here. Our wavelength for blue is here. So red has a longer wavelength than blue, and we would expect red then to have actually lower energy than the blue, as blue has a shorter wavelength, a higher frequency. So sort of the red part of the spectrum where we see color, red, orange, and that part is kind of the lower energy in terms of colors. And kind of the blue, violet, that part of the sort of color spectrum where we see colors is going to be more high energy because of their wavelength are lower. Now, one sort of aspect of waves as they move is basically the speed at which they move. And that is 3 times 10 to the 8 meters per second, or 186,000 miles per second. That is actually a constant. And that is the speed of light, which is c. And that is a number you should know because it does pop up a lot. 3 times 10 to the 8 meters per second. And we could actually use this equation here to help us calculate one of two things. If we know the frequency, we could figure out the wavelength associated with that wave of light, or vice versa. If we know the wavelength, we could figure out the frequency associated with it, and they both equal the speed of light when you times them together. So that is the speed of light is equal to the wavelength times the frequency. Once again, if we put our units in here, it is meters for the wavelength, it is 1/seconds for our frequency, and our speed of light ends up being units of meters per second. So it's really important when you use this equation that the wavelength is in meters, so everything cancels out correctly. We could rearrange it, and it's the same rearranging no matter what you're solving for. So the wavelength is c divided by the frequency, or the frequency is c divided by the wavelength. So those are two rearrangings of that equation. The good news is they're both basically the same calculation. You definitely want to make sure that you use your exponent button, obviously, in a situation like this, so that everything comes out correctly. Why don't we try one here and see? Why don't we do... Let's do, what is the wavelength in nanometers associated with a wave that has a frequency of, we'll do 5.6 times 10 to the 14 reciprocal seconds. Here. Okay, let's take a look. So again, we'll use really the same equation here, regardless if we have the wavelength or the frequency given to us. In this case, we do have the frequency given to us, and we're looking for the wavelength, so we're going to divide this to the other side. and that will give us the wavelength is c divided by the frequency. In this case, c is our constant, which is our speed of light, which is 3 times 10 to the 8 meters per second, divided by our frequency of 5.6 times 10 to the 14 reciprocal seconds. We want to make sure definitely that we use our exponent button here. So that's 3 exponent button 8 divided by 5.6 exponent button 14. That's going to give me, we'll call it 5.4 times 10 to the minus 7. The units here are going to be seconds, and seconds are going to cancel. Going to leave us with meters plus u that is left over at this point. Once again, we wanted nanometers here, so we'll take our conversion, which in this case would mean 1 nanometer is 10 to the minus 9 meters. Again, not the other way around. Doing a little dimensional analysis here, we'll go with a 1 nanometer up on top, 10 to the minus 9 meters on the bottom, so that they cancel. Once again, that basically is 1 times 10 to the minus 9. So we'll divide by that, and that's going to get us about 540 nanometers in this particular case. Any questions on that there? So again, really important, exponent button, when you put it in there, that you get the right answer. If you find yourself just off on the exponent part, it is probably how you're putting it into your calculator. Any questions on that calculation there? Okay. So depending on sort of, as for example, when electrons transition from one energy level to the next, they will give off that energy in the form of a photon. And really depending on sort of the wavelength associated with that photon that's coming off, it may fall in some different parts of what's known as the electromagnetic spectrum. And there's different sort of parts to the spectrum. On the right-hand side, in this particular picture here, we have a longer wavelength, as we talked about here. That would mean a lower frequency and a lower energy associated with it. On the left-hand side, we have a much smaller wavelength. That would mean a higher frequency, and it also mean higher energy. So as we go through the electromagnetic spectrum here, first off, down in this region here, we have radio waves. Again, kind of a longer wavelength, lower in energy, which is why it's not too bad when we listen to the radio and all that in our car. Next to it, we have microwaves, a little shorter of a wavelength, also increases the energy. Again, able to kind of spin water molecules really fast in your food and cook your pizza in like 3 minutes. So you're all good on that. Going to the left are microwaves, we have infrared, which again, the wavelength's getting smaller, a little bit more higher in energy, sort of where we feel heat and stuff coming off. Next to the infrared region is the visible part of the spectrum. That is where we see colors. Once again, that is our Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, violet type colors. And as I mentioned before, there is again a difference in terms of the energy. Around 700 nanometers, we got red, which is going to be lower in energy because it has a longer wavelength. Then say over here at the violet side or purple side, about 400 nanometers, we have a much higher energy as the wavelength is smaller. So even within colors, as I mentioned, there is sort of a difference in energy. So red, orange, yellow, kind of on the lower end, and then into our blues and our sort of violets is kind of higher in energy in terms of the visible part of the spectrum. Continuing past the visible part of the spectrum is their UV. Like we used, I think, UV boxes the other day in lab, right? You turn it on, had the UV light. Why we put sunblock on as well, so we don't get too burnt as we walk outside from the UV radiation, as it's high energy, so it kind of blocks it a little bit. To the left of that, again, shorter wavelength happening here. We got X-rays. Obviously, again, why they give you the lead vest and step out of the room when they shoot the X-rays. It's pretty high in energy. And at the very end of the spectrum there, we have gamma rays, which is basically just pure energy. It's a radioactive sort of particle like alpha, beta. And then there's gamma, alpha being positively charged particles, beta being negatively charged particles, and gamma rays basically having no charge. So kind of like a neutral sort of species, just really high energy. So as we go from right to left on this particular picture here, we're increasing the energy. You do need to know this electromagnetic spectrum. You don't need to know the exact where everything comes off at. You put it in order from like highest energy to lowest energy, shorter wavelength to longer wavelength, higher frequency, lower frequency. That also includes the colors. You need to be able to put the colors in order the same way, high energy, low energy, wavelengths, and so forth. So as we were talking again, these guys will give off and absorb these sort of packets of energy as they transfer from one place to the next in terms of the energy level. And there is a way that we could calculate the energy associated with a wave coming off by really knowing one of two things, either the frequency or the actual wavelength. So this energy on the bottom there is, or this formula on the bottom is the energy is equal to H times V. H is a constant. H is Planck's constant, which is this number right here. And that is a constant number like the speed of light, which is the 3 times 10 to the 8. And this again is our frequency. So if we look at the energy associated, or the units associated with this, H is joules times seconds. So that's what those units are. Joules is an energy unit. Obviously, seconds is a time. And if we times it by our frequency, which is 1 over seconds, the seconds will cancel. And when we use this equation, we will end up with units of joules when it's all said and done, which is good because that's a unit of energy. We can obviously calculate the energy associated with a wave if we know the frequency. We could also tie this equation in with the one that we just saw earlier and just used, which is our C is equal to the wavelength times the frequency, where the frequency is equal to C divided by the wavelength. So we basically could take that whole thing and put it right in for the frequency. And we get another sort of very useful version of this equation, which is the energy is equal to H times C divided by the wavelength. So H and C are constants. So that's your speed of light and your Planck's constant and the wavelength. So this is how, if you just know the wavelength, you could plug it in there and figure out the energy associated with it. Or if you just know the frequency, you can plug it into the original one there, the H times the frequency, and figure out the energy associated with it. Once again, we do want to be careful on units. And for our wavelength here, in this equation here, it does need to be in meters because the speed of light's in meters. So everything will cancel out correctly. So those are two ways you can figure out the energy associated with a particular wave that has a wavelength or a frequency. Any questions on that there? So why don't we try the one we just did there? Let's calculate the energy associated with what we just calculated, which I think was, what do we have there? 4 or something? At 540. Okay. So I want you to calculate the energy in joules associated with a wave that has a wavelength of 540 nanometers. And again, our nano being 10 to the minus 9. Okay, we're going to calculate the energy, which is H times the frequency. Using our substituted version there, we could substitute in HC divided by the wavelength. And again, that comes from this relationship that we saw earlier, that the frequency is C divided by the wavelength. So we're basically just substituting that into here to get to there. Again, the top numbers here are all constants. So that's going to be our Planck's constant, which is the 6.63 times 10 to the minus 34 joules times seconds. Our speed of light, 3 times 10 to the 8 meters per second, divided by our wavelength. Once again, though, we do need to get it into meters. Otherwise, we're going to be off because we're in nanometers here. So we'll do our conversion here to take it back to meters, which I think we had earlier. And again, a nanometer in this case would be 10 to the minus 9 meters. Those guys are going to cancel and give us like 5.4 times 10 to the minus 7 meters. which would go here, 5.4 times 10 to the minus 7 meters. In terms of units, the meters on top and bottom will cancel, seconds will cancel, going to leave us just joules that are left. And if we do that, once again, making sure to use our exponent button, 6.63 times 10 to the minus 34 times 3 exponent 8 divided by 5.4 to the minus 7, going to give us an energy associated with that guy about 3.7 times 10 to the minus 19 joules. Questions on that calculation there? Now, just to show you that, I think in the original question we had back here, we had the actual frequency given to us. So we could have just used the frequency if we actually had the frequency also given to us and just put it into this equation. And just to show you that you should get the same answer here. And putting the frequency in just the way it was, which was 5.6, I believe. 5.6 times 10 to the 14 reciprocal seconds. The seconds cancel. And at that point, you will end up with, should be the same number, 3.7 to the 19. So again, as you can see, all you would need is the frequency, or all you would need is the wavelength, and you could calculate the energy associated with that wave, regardless of which one you have. Any questions on either of those calculations there? Okay, so you should know how to do those calculations, obviously, there. Talk about that. All right, so as we've been talking about, what we're really talking about a lot in this chapter is really those electrons transitioning. And Bohr's theory of the hydrogen atom, as we'll talk about here a little bit, is what's sometimes referred to as the planetary sort of model, where there's sort of a nucleus in the middle and there's these nice orbits, and electrons are basically moving around sort of in these circular patterns. As we'll talk about, it's not really how they move, but this is sort of the Bohr's model. And he basically thought of electrons as either being restricted in a certain orbit. It's either in like this orbit here, which is like the n equals 1 orbit, n equals 2, n equals 3 orbits here. N equals 1, n equals 2, n equals 3. These are basically the energy levels, with n equals 1 being closest to the nucleus, n equals 2, and so forth being further away. So he envisioned sort of these electrons moving around in these nice circular patterns. And as the electrons sort of transitioned, say from a higher energy level to a lower energy level, it would have to give off that energy in the form of a wave that has a particular wavelength associated with it. And what it would do as a result of that is it would give off some type of emission. An emission spectrum is given off as electrons from a higher energy to a lower energy level, because the atom is basically emitting off the energy to allow those electrons to do so. The result of that is, for example, that it looks like a spectroscope with a prism in it. You may be able to distinguish colors coming off, distinct lines of colors coming off as a result of the photons of light that are coming off. Now, spectrum are the spectrum by sort of elements are more of what are referred to as a line spectrum. And the difference between sort of a continuous spectrum and a line spectrum, as we'll talk about, is really sort of the energy that's happening there. So, few ways to put it in fire like you did, use an electrical discharge. It's going to ignite all the electrons and stuff like that. Spectrum is one where, like the sun, for example, everything sort of comes off at once. So you have wavelengths of light coming off at all sort of areas along the way. For example, when we see something that's red hot, obviously the glow is part of the visible part of the spectrum, where we can kind of see colors and stuff glowing. We also could feel the heat coming off, which will be part of the infrared sort of region of the electromagnetic spectrum. So not all electron transitions, for example, will result in energy be coming off in the visible part of the spectrum where we actually see colors and stuff like that. Could come off really anywhere along that spectrum that we saw. Could be in the UV part, could be in the IR part, could be in other parts where you wouldn't necessarily see colors. Like fireworks, we do see colors, right? When you shoot off fireworks, you explode, right? With some explosion, which gives off a lot of heat and energy to the elements that are in the fireworks, excites their electrons, and those guys give off energy in the form of visible light that we go, oh, green color, pretty, blue color, right? Purple colors and stuff like that comes off. So a common feature, though, of the sun and heated solids is that you have this sort of continuous spectrum that comes off. And if you remember, we talked a little bit about quantized energy and the idea that it's like stairs. You can kind of think of a continuous spectrum, kind of like a ramp that you're walking up, and literally on a ramp, right? You could pretty much lay it up anywhere, right? You could stop at any point along the way. You don't have to be at a certain level. And that allows everything in terms of wavelengths to come off at once. This is what you kind of see with the sun, like a rainbow type of effect, like everything coming off basically all at once. And that's different than how elements are. They are more quantized, which means you're either there, there, or there. As we talked about, if you're walking upstairs, you're not going to stop halfway through. You're either going to have enough energy to go from this level to that level. And the result of that is when we heat elements, especially in the gas phase, we see more of what's referred to as a line spectrum. And because they has to be on this level, or they has to be on this level, or the transition from one level to the next has to be complete, we end up getting these very distinct lines that occur if you look at it through a prism like a spectroscope. And they obviously occur at different colors, not just that color, but they occur at different colors and different wavelengths. And elements, so spectrum, particular element, and based on the lines that you see, at, it has its own sort of unique spectrum as to what lines you see kind of highlight as the electrons are transmitting. Here is the emission spectrum for hydrogen. So like hydrogen in its gas phase, again, if you do an electrical current through it or do something to it, it will give off these sort of 4 distinct sort of colors at these wavelengths. And as you can see, they are lines, so there's specific one. And each of these little lines represent a transition of an electron in hydrogen from one energy level down to the next. So that is what we're seeing here, this sort of quantized transition that occurs. And for example, we have like a red, right, versus over here, which is more of a purple or violet color. And earlier we talked about energy here, right, between, say, these two colors. The one that is lower in energy would be which one? It'd be the red, right? This would be a little bit higher in energy. So what we're talking about is we have these electrons at these different energy levels, you know, say n equals 1, n equals 2, n equals 3, n equals 4, and so forth. And let's say we had an electron that was on the 4th energy level and it decided it wanted to come all the way down to the 1st energy level versus that was maybe in the 3rd energy level and decided it wanted to come down just energy level. And my made up example here, which we'll use hydrogen's lines here for our question, that's obviously not hydrogen's exact transitions, but the one that went from the 4th energy level all the way down to the 1st energy level, would it be represented, do you think, by the line on the left or the line on the right? We'll start with, if I went from the 4th energy level all the way down to the 1st, does that take a lot of energy to do or not a lot? It would be a lot of energy, right? It's like, if you want to think about the stair example, you walk down 4 stairs basically, right? So a lot of energy to come down the 4 stairs. That should be a lot of energy, which means the wavelength should be long or short? Short, right? And in terms of colors and short colors here, it would be more the violet one here, right, in our example, as opposed to my electron that went from the 3rd energy level to just the 2nd, right? That's like going down just 1 step, right? not a lot of energy needed to go down one step, which means it'll be lower in energy, right? Which means the wavelength should be longer, right? And in this made up example here, that would probably maybe correspond to the red color we see. So each of these are basically a result of these electrons transitioning. You can make a fairly good guess just based on the colors that you see and their positions as to sort of maybe how far that electron is maybe transitioning. Obviously, it's moving a lot of different energy levels. It's going to require the atom to give off that amount of energy, right? A good amount of energy for those electrons to come down. That would result in a lower wavelength in terms of the wave coming off, as opposed to just an electron making a smaller transition, which would allow the atom to release a lower amount of energy, and that would have a longer wavelength associated with it. Any questions on that there? So Bohr's model of the atom, as I mentioned, is this sort of planetary model where he thought basically, again, electrons were sort of transitioning around the nucleus in these orbits. Again, they're restricted to sort of these orbits, and they can only transition from one energy level to the next. It works really well with hydrogen, which actually only has one electron, but his theory sort of falls apart as you get multiple electrons sort of involved. And when you get multiple electrons involved, you have a lot of electron and electron repulsions that occur because electrons are negatively charged. So it doesn't work very well for all things past hydrogen. Let's sort of describe like we sort of the lines of those electrons from one energy level basically to the next. Again, the idea here is that they are in those fixed orbits about the nucleus. And as an electron would transition down to a lower energy level, again, the atom would give off that in a form of a wavelength, which, as we just talked about, you could calculate the energy associated with that by using our equation there that we just did an example of, if you know the frequency or even if you know the wavelength, as we did in that calculation. Here's a prettier picture of that. And again, each of those lines resulting from those electrons being dropped down from a higher energy level to a lower energy level. Speaking of energy levels, that is what is sometimes referred to as quantum number, or the principal quantum number. And it is the n number, and n is the principal quantum number. And it can have values of 1 through 7, where n equals 1 is the ground state. And anything kind of above that, 2 through 7, are referred to as excited states. The ground state is closer to the nucleus. Anything above that is getting further from the nucleus. So n equals 2, 3, 4, 5. And we're getting farther and farther away from the nucleus. Quantum number, yeah. Yeah, it would be the lowest energy level. In the case of Bohr, it would be like the first little orbit right around the nucleus. N equals 2 would be the next one, third one. Even again, they don't really work in orbit. To Bohr, in general, we talk about as being sort of the lowest energy level, closest to the nucleus. So those are electrons on that first energy level are really kind of right there next to the nucleus. And then you kind of build out away from it. As we'll talk about, they really don't travel in pretty circles, but they're still traveling randomly in that empty space around the nucleus. And the sort of their distance from that nucleus is sort of the n equals 1, n equals 2, and so forth. Other questions? Quantum numbers, there's really 4 different types of quantum numbers that you'll talk about when you get into 1A, but we're just going to kind of stick with that for now. We'll talk a little bit about it maybe next time as well. So as I mentioned before, those 4 lines that we see is really a result of those electrons transitioning. And once again, this little guy here that just went 1 sort of transition there in the middle would probably result in a lower energy, longer wavelength than our guy here that went from here all the way down, basically to the bottom, which will give us a shorter. This is the idea of quantized energy and continuous energy. Again, all the way through all kinds of wavelengths happening. Where electrons will be are transferred from one energy to the next level. There's our staircase, for example. So Bohr's model, as I mentioned, worked really well to describe what's happening with electrons and their transitions in hydrogen. But further experimentation and even sort of theories that came out after that basically kind of moved us away from the idea of Bohr's model of this sort of planetary model and orbits. And like the idea of orbits is, you know, the electrons going around in a circle, which means I could put my finger there and eventually, right, it's going to come back around and it should be there, which means we have a pretty good idea how it's moving, where it will be. If we just wait long enough, it'll come back around the circle and stuff like that. A lot of experiments and theories, starting with de Broglie here, came up with the idea that particles like electrons will have wave-like functions, and they really don't sort of travel in these nice pretty orbits and nice pretty circles and stuff like that. So de Broglie's idea, which was actually just an idea, he actually didn't do any experiments, he just came up with it. People later did experiments and said, sounds about right. He came up with the idea that, you know, particles, for example, like electrons, could behave like wave functions. And he came up with this idea of sort of like the standing wave, and it's like a guitar string. If you pluck a guitar string, right, you'll see the wave, but really, obviously, it can't go anywhere because it's like attached to the guitar, right? So the string is not going to pop off or anything like that. And that's sort of the idea here with a particle like our electron, where there is obviously going to be some attractive force between the electron, which is negatively charged, and the nucleus, which is positively charged. And it will be able to have this sort of wave-like function where it's really tied to the atom through its attractive force to the nucleus, kind of like the string on the guitar, but it can still move and vibrate around like the guitar string could move around, and the electron could vibrate and move around in that empty space outside the nucleus. But it is still sort of restricted in sort of where it can move around. There's also in a wave places where there's no amplitude, and those are what he referred to as nodes. And those are sort of places where it gets really kind of close to the nucleus. So some points along the string were called nodes. They do not have any amplitude. These nodes at each end, and there may be nodes in the beginning, in the middle as well, between the ends, again, like if your string was on the guitar there. Basically, the idea here was he reasoned that waves can behave like particles, and again, particles can exhibit wave-like functions, which is really moving us away from Bohr's model of the orbits and these nice pretty circles at which they are moving. A really big sort of move away from Bohr's idea came with Heisenberg and Heisenberg's uncertainty principle, which basically says it's impossible to know simultaneously both the momentum and the position of a particle with any type of certainty. So the idea of Heisenberg is the more you know about the momentum, the less you know about the position of a particle, and vice versa. The more you know about sort of the position of a particle, the less you know about how it's moving. And that's basically totally different than Bohr's idea of, well, I know they're in circles, they keep moving around this way, so I definitely know where they should be and how they're moving. To this idea that we really don't know how a particle like an electron is moving. It is moving really randomly about the nucleus in some type of pattern. So we're moving away from the idea of orbits. That we could do is this idea of what are referred to as orbitals. And this is based on what is referred to as Schrodinger's equations, which is a bunch of calculus type equations. And if you ever take physical chemistry, you'll do all those equations. Save it to the end. Everybody says physical chemistry to the end. But the idea that sort of came out of this is the transition from Bohr's model of orbits to, like, I know for sure is traveling a pretty circle, to this more wave mechanical model of, I think electrons are in what are referred to as atomic orbitals. And what are atomic orbitals? Atomic orbitals are essentially probability maps, where you say, I think it's a pretty high probability that I can find an electron here in the atom. I'm not really sure how it's there, where it got there, how it's moving, but I think there's a reasonably high probability that in this atom I could find an electron in this location. Now, the high probability to find an electron would probably be near the nucleus, again, because of the opposite charge. And as you sort of fan out from the nucleus, the probability of finding an electron does start to decrease. When we talk about atomic orbitals, as we'll talk about here, there's a few different types. There are s orbitals, p orbitals, d orbitals, and f orbitals. And these are all atomic orbitals. They are essentially based on Schrodinger's equations, probability density maps of within an atom. This is a pretty high probability of finding an electron there. You know, like if you went to a driving range for golf, there's a high probability of finding a golf ball on the grass in front of the driving range, right? So could be like right in front, could have a whole bunch in front, could have some just shanked off to the right in the parking lot. Hopefully a less of a probability if you shake it into the parking lot, maybe not, I don't know, depending on your golf game. But you know, there's a lower probability that if you park your car, it's not gonna get hit by the golf ball based on its location, right? So that's sort of the idea with electrons. I know we've all put it in the parking lot once or twice, maybe more than twice. So this is sort of the idea of a probability map for electrons. And obviously the darker area is a higher probability of finding an electron. Lower, kind of lighter area, less of a probability. Nucleus is kind of thought of being kind of there. So you can see kind of dark. And as we sort of travel some distance out from our nucleus, we see the probability starts to decline. Does it mean we can't find an electron there? No, it just means there's probably a less of a probability of finding an electron there than, you know, closer to the nucleus. Again, like my bad golf example, higher probability of finding the golf ball in the grass than say in the parking lot, right? But there's still a good probability that you might find a golf ball in the parking lot as you walk through it. Hopefully not near your car, I would hope, yeah. So that's the same idea. Much like my golf ball example, not sure how that golf ball got to the parking lot, right? Nobody knows how it got there. Nobody knows the route it took. It just happened to end up there, right? It's not the guy running away really quickly with his golf clubs holding on to him. So let's talk a little bit about these atomic orbitals. There are different types of atomic orbitals, and the first type is an s orbital. And s orbitals are spheres. So they're basically circles, and we do find s orbitals on every energy level. So starting with the first energy level, which is our n equals 1, which is closest to the nucleus, we have what is referred to as a 1s orbital there. When we go to the second energy level, we have what is referred to as a 2s orbital. We go to the third energy level, we have a 3s orbital, and so forth. So on every single energy level that we have, there is always an s orbital. The first number where it says 1s, 2s, 3s, that is the principal quantum number. That is the energy level at which that orbital is at. So a 1s orbital is on the first energy level, and it's an s orbital. A 2s orbital is on the second energy level. It's also an s orbital. They are the same shape, but they do get larger as you go up energy levels to accommodate more electrons. So the circle kind of gets bigger and bigger to house more electrons in it. One really important thing about orbitals, be it a s orbital, p orbital, d orbital, f orbital, all individual orbitals could hold a maximum of 2 electrons. So no matter what orbital it is, an s orbital, p orbital, d orbital, if you have an individual orbital, it can only hold a maximum of 2 electrons in it. So here's a picture of an s orbital. Here's sort of the density diagram, and they kind of close the circle to get us to here. And again, it basically is the shape, and it just increases with size as we go up energy levels to accommodate more electrons. Once again, these are really theoretical probability maps. Are you going to find a circle or a a figure 8 in an atom, probably not. But these are, again, sort of these mathematical probability maps of finding electrons in an atom. The next type of orbitals appear on the second energy level, and they are what are referred to as p orbitals. And unlike s orbitals, there's actually 3 different types of p orbitals. There's a px, a py, and a pz orbital. And that's like in math. There's an x, y, and z axis, and there basically is one on the x, one on the y, and one on the z in 3-dimensional space. Basically, a p orbital, figure 8, or teardrop sort of shape, with kind of like the nucleus being thought of as being about there, and the high probability of an electron kind of in this area of the lobes there of our orbital. Now, the p orbitals do not appear until the second energy level. So on the first energy level, there is just the 1s orbital. On the second energy level, there's the 2s orbital. And this is where we start to see the 2 p orbitals appear. It is made up of 3 individual p orbitals, the px, py, and pz orbital. If I take all 3 of those orbitals together, if I take all 3 of these orbitals together, how many total electrons could I put in there? I could put 6. I could put 6 electrons, and these 3 p orbitals all together is what is sometimes referred to as a subshell or sublevel, depending on your book. So the 2p subshell, which is composed of 3 individual p orbitals, px, py, and pz orbital, could hold a maximum of 6 electrons. Basically, if each of those lines are the orbitals, 2 electrons in each, basically. An individual 2p orbital could hold how many electrons? Still only 2, an individual p orbital, right? So individual 2p orbital can hold 2. The 2p subshell, which is all 3 of them together, 2 times 3 is a 6 total electrons that could happen there. The next type of orbitals that are important appear on the 3rd energy level. And by the way, this is what the p orbitals look like. They are figure 8s, and here's our density map again with sort of the nucleus being there. You see the highest density of electron probability sort of near that nucleus at that point. Z in terms of 3-dimensional space. The next important orbitals are d orbitals. 5 different d orbitals. And the d orbitals do not appear until the 3rd energy level. So once again, on the 1st energy level, we have our 1s. I'll go up here. We have our 2s, our 2p. And then on the 3rd energy level, we have a 3s, a 3p, and this is where our 3 d orbitals first start to appear. All 5 of those 3 d orbitals is a 3d subshell. Our level, our sublevel. If I max out the d subshell, how many electrons can I put in there? 10, right? 2 in each, and there's 5 of them. So we could put a maximum of 10 electrons in that 3D or any D subshell that we have, 3D, 4D, or so forth. The next important orbitals is actually the F orbitals. Not sure where that slide went, but we'll throw it in here. F orbitals, there are 7 different types of F orbitals, and they start on the 4th energy level. So once again, on the 1st are 1s, on the 2nd, 2s, 2p, on the 3rd, 3s, 3p, 3d, and on the 4th is where we start to see 4s, 4p, 4D, and 1, 2, 3, 4, 5, 6, and 7. I'll squeeze it in there. R4F. And once again, that would be the 4F subshell that could hold a maximum of 14 electrons if we filled up every single orbital in there. Single orbital in there, you do not. To max it out, you would have to 14 in there. Electrons go into the atom, lowest energy first, and then continue to fill next lowest, and next lowest until all the electrons will basically be distributed. We talked about the subshell. If we take, for example, something like the n equals 3 here. On the n equals 3 level, that is what is referred to as a level or a shell. If I want to max out the electrons on the n equals 3 level, how many electrons could I put in there? Well, the n equals 3 level would be everything in the red box. That would be this guy, which you call 2, 4, 6, 8, 10, 12, 14, 16, and 18 electrons if you filled up everybody on that level. How about the n equals 2 level? How many electrons in there? It would be 8. The n equals 2 would be everybody on that second energy level, which would be 2, 4, 6, and 8 electrons if we fill them all up. Nobody wants to draw all this, so there's a quick way you could calculate maximum number of electrons on a level. It is 2 times n squared. N is the energy level. So if you did the one we just did before, n equals 3, 3 squared is 9, 9 times 2 is 18. Second energy level, 2 squared is 4, 4 times 2 is 8. So you want to do the squaring part first and then multiply by 2, and I'll give you how many electrons. So if I was on the 6th energy level, how many electrons could I put in there? 6 squared is 36 times 2 is 72. 72 electrons, yeah. So I can put in there. Any questions on that there? Okay. So let's talk a little about the energy of these electrons. Because they go in basically one at a time, lowest energy to next lowest energy. When we're dealing with hydrogen that has only one electron, what we see is the energy of all these orbitals, they're equal to each other. What I mean by that is everybody on the second energy level here, it's all equal to each other in energy. Everybody on the third energy level here is all equal to each other. When we start putting more and more electrons into the atom, we run into a little problem of electrons are negatively charged and there's more electrons which are negatively charged. Do they really want to be near each other? The answer is no, they really don't. But because they're kind of tied to the nucleus, right, they can't leave in most cases. So they have to kind of move around and spread around. And it does affect the energy of the individual orbitals and the order at which they go in. So when we get more than one electron, we see this kind of shift in the order of these orbitals. And the major shift happens right around here. It goes like you would imagine 1s, then 2s, then 2p, then 3s, 3p. After 3p, it actually goes to the 4s orbitals first. They actually end up being lower in energy. Then it goes to the 3d, and that pattern happens up here, 5s first, then into the 4d. So it's really important to know the correct order at which electrons go into the atom so that you can write electron configuration. If you know the correct order and you know that S's could hold 2 electrons, P subshell 6, D subshell 10, F subshell 14, you'll be able to write any electron you want. This is actually the order at which electrons go into the atom. We always start up here. And we basically follow the arrow to the end, and then we zigzag back around and follow the arrow to the end, and we continue that pattern. Here again, the S of maximum of 2, P subshell 6, D subshell 10, F subshell 14. It's also really important to remember, as we talked about, that on the first energy level, there's just S's. On the second energy level, that's when P's occur. On the third energy level, that's when D's occur. And on the fourth energy level, that's when F's occur. Because if you remember that, you frankly can recreate this yourself on the paper by going first energy level 1s, second energy level P's, third energy level D's, fourth energy level F's. And pretty much all you have to do is just fill in the numbers underneath each of these. So this would be like 2s, 3s, 4s, 5s, 6s, 7s. This would then be 3p, 4p, 5p, 6p, 7p, 3d, 4d, 5d, 6d, and 5f. And really quickly on the piece of paper, you could basically recreate that for yourself. All you have to remember is 1, 2, 3, 4. Just put the numbers down underneath there. Any questions on that there? So if you know those two things, like I said, you really can write any type of electron configuration you need to. So let's talk about writing electron configuration and what it is. Electron configuration tells us how the electrons are distributed in the atom, what orbitals they are in, what energy levels they are on. If we are dealing with something that is neutral, then the atomic number, which is the number of protons, as we talked about, will also tell us the number of electrons there are. And we could basically do that and write our electron configuration accordingly. So let's take a look here. Why don't we start with number 1, which is hydrogen. Hydrogen's atomic number is 1, which means if it is neutral, it has 1 electron and it should have 1 proton. So 1 electron is important. We would start at the very top of our little chart there, and we would go with 1s1 is how that is worded, would be the electron configuration for hydrogen. The 1s1 is written like that, big 1, little s, and superscript 1, maybe not that big. First one is the energy level, the principal quantum number. So that's on the first energy level. The S tells us we're hanging out in the S orbital on that energy level. And the superscript 1 is how many electrons there are in that particular energy orbital or subshell. There's no dashes, there's no commas. It's just 1s1 is how you write it. Another way that we could represent electron configuration is what is referred to as orbital diagram. And in an orbital diagram, you use boxes or lines to represent the orbitals, and you use arrows to represent the electrons. So if we were to draw the orbital diagram here for hydrogen, we would show 1 electron, and always the first electron that goes into the orbital will have this sort of arrow pointing upwards. It actually represents what is known as the spin quantum number, which is ms, and it has a +1/2 is usually denoted like that. There are actually 4 quantum numbers. We don't get into too much of it here, but we saw n, which is really our energy level. There's L, which is really the orbital that the electrons are in. M sub L is the how many of the orbitals there are. And really, the real definition is actually the orientation in 3-dimensional space, like a px, a py, and a pz type of orbital. And M sub s is the spin quantum number, which could be +1/2, which means the arrow points up, or it could be -1/2, which means the arrow points down. So I mentioned the 4 quantum numbers because it's actually important for what we're going to talk about next, which is what do we do with the next electron? So in this s orbital, we could put 1 more electron in there before it's filled. And there's really a couple of options you could do. You could either put it in going in the same direction, or you could put the electron going in the opposite direction. And there actually is a rule that we follow, which is known as Paulie's exclusion rule. And Paulie's exclusion rule basically says that no 2 electrons in the same orbital can have the same 4 quantum numbers. So you may be saying, How are they different? So how they're different is if we take our helium, or we don't take helium, but we take helium, which is number 2 on the periodic table, its electron configuration would be 1s2 basically. So we're going to fill up that s orbital. We already with hydrogen took our 1s orbital and we put our electron upwards. Now, as I mentioned, we could take our next electron and go up and up, or we could take our next electron, go up and put the next one down, basically. So what makes it different here is this. If we were to do the 4 quantum numbers for this particular electron here, which is this electron, and also this electron. Not that you need to know how to do this at this point, but let me just tell you what the 4 numbers would be. N would equal 1, L would equal 0, M sub L would equal 0, and M sub S would equal plus 1/2. So these are what are referred to as the 4 quantum numbers for basically our electron pointing upwards in this case. Now, clearly, if I decided I wanted to put my next electron like this, that is pointing the exact same way in the exact same orbital, which means it will end up with the exact same 4 quantum numbers. And that is what Paulie's exclusion rule says is a violation and cannot occur. So because they would actually end up with the same 4 quantum numbers, we cannot put our next electron pointing in the same direction. Now, is it really different, this guy here that's pointing downward? Well, if we were to do this guy's numbers here, this guy's numbers would be, if I get something right with here, there we go. This guy's number would be n is equal to 1, which looks the same. Its L would equal 0, which looks the same. Its M sub L would be 0, which kind of looks the same. But now the spin here is not pointing upwards, which is plus 1/2. It's actually pointing downwards, which is considered minus 1/2, which is the major difference between those two. And by putting the electron sort of pointing downward in terms of a spin, electrons have their own spin affected by magnetic electrical field. It does not violate Paulie's exclusion rule because now both of those electrons, a slim difference that it is, it's just a spin, is different. They now have different quantum numbers, both of them, and they do not violate Paulie's exclusion rule. And that would be the correct way to do it for something like helium, where it would be 1s2. We would put our first electron in upwards, and then our second electron goes downward. That basically tells us they have different quantum numbers, and that will not violate Paulie's exclusion rule. So for us at this point, that's all you have to remember: 1 up, 1 down, same orbital, first one up, second one down. This arrangement where we basically have opposite spins on our electrons is what is referred to as being paired spin. They kind of cancel each other up, 1 plus 1/2, 1 minus 1/2. They sort of cancel out their effectiveness on the atom by being paired off like that. Any questions on that there? So continuing on here to number 3 on the periodic table, that is lithium, which would be 1s2. We no longer have any more room in that box as we saw. We then need a zigzag back, and the next orbital you would go to would be the 2s orbital, and we would go with 2s1 in this case. This means on the first energy level, how many electrons do I have? I have 2 on the first. On the second energy level, I have 1, yeah? So I have 1 electron on a higher energy level, and I have 2 electrons on a lower energy level. And if we were to do our orbital diagram, we would need 2 boxes. One represents the 1s orbital, one represents the 2s orbital. And by the way, I'm just going to go to the right. Truthfully, if you did this correctly, you would go up in terms of energy, right, to show the energy difference between them. But I will run out of room, obviously, on my page, so I'm just going to go to the right. But normally, you know, you would have like, if you properly did it with the right energy, it would look, you know, like this, right? The 1s, and then the 2s is higher in energy and so forth. First one goes in, second one goes down, next one goes up. Yeah, we can now see we have room for 1 more electron there in our 2s orbital before we would have to move on. So if we do that, let's go to number 4, which is beryllium. Be 1s2, 2s2. At this point, we now have 2 electrons in the second energy level, both hanging out in the s orbital. We have 2 electrons in the first energy level, also hanging out in an s orbital. Our orbital diagram here would be something that looks like this: up, down, up, and then down in terms of that. At this point, we've now filled up our 2s orbital. Now, electrons would have to go into what orbital after that? After 2s, if you follow the little zigzag, we come back, it comes to 2p next. So that would be the 2p orbital. And to show you that, that is going to be boron, would be 1s2, 2s2, 2p1. In this particular case, how many electrons are in my second energy level? It is 3, all 3 of these. 2 here and 1 here gives me 3 electrons in the second energy level. And we obviously have 2 electrons here in the first energy level. In this case, we would actually need 3 boxes for our p orbitals. This would represent the px orbital, the py orbital, the pz orbital. And it would go up, down, and the very first one in the p subshell here will go up in the far left there. And at this point, how many more electrons can I put in that 2p subshell before it's filled? You put 5 more, right, before it fills out. We now run into another important aspect of this, which is, where do I go with my next electron, right? I have a couple of options. I could, with my next electron in that 2p, end up pairing it off. I could not pair it off and go next door. And there actually is a rule that tells you which way you should do it, and it is not this way. The rule that tells us what we should do is what is referred to as Hund's rule. And Hund's rule basically says that the most stable arrangement of orbitals is one that maximizes parallel spins. So if you remember, we saw earlier that if we put electrons going in opposite directions, this is what is referred to as paired spins. Electrons all heading in the same direction is what is referred to as parallel spins. So what we would do is, basically, when you run into a p subshell which has multiple individual orbitals, a d subshell which has 5 individual orbitals, or an f subshell 7 individual orbitals, we always fill the orbitals like this. When there are multiple ones in the subshell, we always do one at a time, left to right, and then we come back when we have no other options and start pairing off. So one at a time across until we run out of room, and then come back and pair off is how we would do that. So when we get to something like carbon, for example, which is 6, it would be 1s2, 2s2, 2p2. And we would have our orbital diagram here: 1 up, 1 down, 1 up, 1 down, 1 up. And now our next one would go right next door into the py orbital. The pz orbital will then get 1, and then we'll come back and start pairing everybody off. So those 2 aspects of sort of how you draw your orbital diagram are important. 2 electrons in the same orbital should always be paired, opposite spins. When you have a subshell that has multiple individual orbitals, everybody gets 1 at a time going in the upwards direction. That maximizes the parallel spin, and then comes back basically and pairs it off. Any questions on that there? All right, we would lay it up there for today.